day after the midterm.
Yeah, I have to admire the lack of people. When do you think the midterms will be graded by?
I'm aiming for Tuesday. Usually I give them back a week after. I haven't looked at them yet though, so I'm gonna start tomorrow and then probably grade the rest on Monday. Might just be you. Dominic's not even in the class. He's studying for the next class. All right, it's 4 o'clock. Let's go and get started. Good afternoon, everybody. Day after the midterm. So yeah, I kind of expected this to happen, but here we are. Okay, so now that the exam is done, you know, we are pretty much in the last stages of the class. So I have a couple more topics to go over with you guys together. You know, of course, you know, I can't test you on it, so there's no more exams, but you know, I figured these next few lectures are kind of mostly just kind of interesting biological things. So now that we kind of have, we're at this point in the class, you guys kind of have this background of what cardiovascular flow is like. We've done quite a bit of cardiovascular biomechanics. We've done quite a lot of modeling. You know, but I want to kind of finish up the picture in terms of some extra kind of biomechanics, biological stuff. So so for the next 3 lectures, I have kind of some things planned. It's mostly just for your information, for your interest. Of course, you know, it all relates back to, you know, everything else that we've covered in this class. But, you know, it's not directly related to your project and not, you know, directly related, obviously, to the exam, which you've already taken.
Oh
so,
my God.
oh, go ahead. Sorry, someone talking? All right. So that's my plan for the next 3 lectures. So today and both the lectures next week, I'm going to go over I just have some slides prepared to you know, for some interesting stuff. And then after that is going to be our last week of lecture. So our last week of lecture, I don't have anything planned for that week. I want that week just to be focused on just the project. So for the last 2 lectures in week 16, you know, I'm basically just having open office hours. And so I highly encourage you guys to kind of get started on your projects before then. You know, if I gave you feedback on your midterm project to you know, fix some things up with your model, I would definitely get that cleared up before the last week. I would definitely have a mesh before that last week too, just so I can kind of help you with your simulation, right? But at this point, you know, we're in final production, so there's not much left, not that much else left in the class. It's just kind of tying up some loose ends and turning in the final project. Okay. All right, any questions I can answer before we get started? Okay. So I haven't looked at your guys' exams yet, but I am planning to grade them by Tuesday, and so you can expect to come to class on Tuesday to pick them up. Okay. But of course, you know, your grades will be on Canvas, so you know you don't have to pick it up. All right, so the topic for today is going to be venous biomechanics, right? So everything that we've been discussing in the class, all of the physics, all of the disease and stuff like that, those are all on the arterial side of the cardiovascular system. So if you remember from kind of very early on in this class, arteries are the blood vessels that take blood away from your heart, right? You know, when your heart contracts, it pumps, it kind of pushes blood out. It first goes to the arteries. And so inside your arteries, you have much higher flow rates, much higher pressures. You know, most of the diseases that we associate with the cardiovascular system happen in the arteries. So the veins don't really get a lot of attention because they're kind of boring at the end of the day. But you know, I did want to spend at least one lecture kind of talking about the veins, you know, because their physics and kind of the biomechanics of the flow inside the veins is quite different than the arteries. And there are some diseases and some conditions that are you know, specific to the veins, right? But compared to the arteries, we actually don't know that much about them just because it's a lot harder to image the veins. It's a lot harder to kind of get some good, reliable kind of CT scans, MRIs. So, there's just not that much information out there compared to the arteries. Okay, so before we begin, let's kind of remind ourselves what the veins actually do, okay? So like I mentioned, we've been focusing mostly on the arterial system, which takes blood away from the heart. It takes it to your muscles, to your organs, provide the oxygen and nutrients to your muscles and organs that they need to function. The veins provide the opposite function. So they collect blood. So after your muscles and after your organs are done kind of extracting the oxygen and nutrients from your blood cells, usually what happens then is that your muscles then kind of any kind of waste products or any kind of carbon dioxide that's produced by the by your muscles and veins, it then puts them back in the blood, and then the veins then carries the blood back to the heart, back to the lungs, throughout the entire circulation. Right. So one way you can think about it is that the veins serve the purpose of collecting the blood after it passes through your organs and bring it back to the heart. So it's more of a collection system more than a delivery system, right? Arteries are the delivery system, veins are the collection system. Veins also act as a very large storage unit. And so you have a lot more veins in your body, and the veins are a lot more numerous. So just naturally, just a very large portion of the blood volume is stored in the veins at any given time. So anywhere between 60 and 80% of the blood volume is stored in the veins, right? Just basically just on its way back to the heart. Since it's much further away from the heart, it has much lower pressures. So the blood, kind of like we talked about before, when it passes through your capillaries and your muscles and organs, it loses a lot of the pressure because it takes a lot of pressure to kind of squeeze the blood through the capillaries of your muscles and organs. So naturally, the flow in the veins is much slower, okay? Much slower and much lower pressure. And because of that, because the venous flow just has a lot less energy to it, it's very strongly influenced by your posture. And so, you've probably all been there where you kind of sat in a weird way, or you kind of sat on your arm, or you kind of, held a certain posture kind of in a weird way, and your muscles kind of feel all tingly. That's not because the blood is struggling to be delivered there. It's because blood is kind of pooling in that area, and the veins aren't able to return the blood from there. Okay. And like I mentioned, there are some diseases that are specific to the veins. So probably you guys have heard of some disease like varicose veins or deep vein thrombosis. So we'll talk about that today as well. Okay. But kind of the summary here is that the veins are responsible for collecting the blood, and the blood flow is a lot slower and a lot lower pressure in the veins. Okay, so let's talk about venous composition and compliance. Okay, so this is an issue that's there for arteries, but because the pressures in the arteries are much higher, you see much less of this effect. Okay. Okay, so like we all know, up to this point, your blood vessels are very flexible tubes, right? So they're able to kind of bend and contort and squeeze and expand and contract, right? Up until this point, we've talked about the compliance of the arteries in terms of wave propagation and pressure waveforms, things like that. Okay, for the veins, like we mentioned, the pressure is much lower in the veins. And so one thing that's measured a lot is something called transmural pressure. And so transmural pressure is just simply the difference between the pressure of the fluid inside the vein, so that's the pressure internal, minus the external pressure on the veins. Okay. And you may be wondering, where does this external pressure come from? So the internal pressure is pretty clear, just because we have fluid in there, and whenever you have a fluid inside of a system, it has to be pressurized to some degree, right? Where does this external pressure come from? Well, this external pressure is applied by the surrounding tissue. And so your blood vessels, this goes for your arteries and your veins, are deeply embedded within within the tissue inside your body. They're surrounded by muscle, they're surrounded by the organs, surrounded by other soft tissue, right? And being embedded in these systems places some kind of external pressure on them, okay? And this external pressure can change, right? Depending on the posture of the body, or depending if your arm or your limb is under some pressure, right? So this external pressure can change quite a bit. Okay? And because veins typically have a much thinner wall and much larger diameters, the difference between these two pressures often causes the vein to deform, right? In fact, there is a phenomenon known as venous collapse. And so if you put enough external pressure on a vein, you can actually kind of cut it off completely. And so, yes, I'm for it here. So, if you put enough pressure, so let's say that, you have your vein, it's a nice circular shape here, but let's say that, you take your arm and you kind of like pinch it for a long period of time, right? So when you pinch your arm, basically you're putting pressure on the veins, right? So you're putting forces in this direction. Normally for an artery, if you put pressure on an artery like this, you have to put a lot of pressure in order to kind of collapse it. But for a vein, it's very easy just because the internal pressure in the veins is very low. And so what happens then is that if you keep applying this force, this entire vein is going to collapse on itself, right? And then eventually you kind of get this like kind of dumbbell shape like this, right? Where the blood only has kind of a very small portion to pass through. Or in some cases, the blood flow in the veins may get completely cut off. And so if you maintain this for a long period of time, that's when people kind of say like, oh, the circulation was cut off to my arm or something like that. And that's when you feel kind of that tingly sensation. Okay. So there's a model for this. There's an equation that exists for this venous collapse. And it's given by this equation here. Okay. So basically, if this kind of a quantity here is positive, right? So we have a greater external pressure than internal pressure, then you could have collapse. But another way to compute that is that you can take the E, the Young's modulus of the venous wall, H is the wall thickness, R is the radius, okay? And if you compute this quantity here, then this can give you some insight on if it's going to collapse as well. I'm sorry, I kind of misinterpreted it. So actually, what you need to do here is you need to take this quantity, move it to the other side of the equation, right? And if that quantity there is greater than zero, then you're going to have venous collapse, right? Basically, what this equation is saying is that if the external pressure has to overcome kind of two things in order for the vein to collapse. It has to overcome the internal pressure of the fluid that's inside the vessel itself. And then it also has to overcome kind of structural rigidity of the vessel wall itself, which is given by this equation here. Okay. So this part right here is the structure or the strength of the venous wall. Okay. And if the external pressure that's applied either by kind of some kind of external force or even just by just the muscles themselves, if it exceeds both of these things, then the vein is going to collapse. Okay. And then images of the venous collapse are given in this next figure. Okay. All right, any questions on this so far? Okay. Okay. So let's talk about kind of the the pressure area response. Okay. So what we talked about so far is just the phenomenon of the veins collapsing. But obviously, there's some stages that happen before that, right? And so it's not just a black and white thing where like, all of a sudden, if you apply enough pressure, your vein just goes to here, right? There's a progression to this where the cross-sectional area changes as the pressure increases on the vein, okay? And that's what this formula is given by here, right? And so what we have here is what's known as kind of a tube law relationship, which, under some assumptions, so if we assume that the vessel has a thin wall, then we can make a mathematical expression for the relationship between the pressure difference, basically these two things, and the cross-sectional area of the vessel itself, right? So these two are related by this equation right here, right? And of course, we have some parameters here, Kp. This is the bending stiffness of the vessel, right? And if you plot this out, what you'll see is a relationship that looks like this. And so for certain pressures, you have a relatively stable relationship between the cross-sectional area and the pressure difference. But once that pressure difference kind of exceeds a certain point, right? And so once it kind of gets past this -5 threshold here, then this is when venous collapse happens, right? So you can see that the cross-sectional area rapidly decreases here. And so this is right here, venous collapse. Okay. So venous collapse, it's a very important quantity, just because it's, you know, if you collapse the veins, you know, and it's kept collapsed for a long time, then that can kind of cut off circulation or prevent, or I should say, prevent blood from returning to the heart in certain areas of the body. All right, so I think these were done. So these numbers look really clean. So these look like they were done by a simulation. I don't remember exactly what study this comes from, but I'm sure they've also validated it within real life measurements as well. Okay. All right, so let's talk about the blood flow in the collapsed veins. And so you can imagine that when the veins collapse, it's going to be a lot more difficult for blood to flow in there, right? Because we already know that this relationship exists where the viscous resistance of blood flow flowing through a vessel strongly depends on the radius, right? And if you collapse the vein, collapsing the vein is basically the same thing as decreasing the radius by a large amount, right? And so if the radius goes down, you can see that the resistance is going to go up by quite a bit. Okay. And so, you know, you don't have to have complete venous collapse in order to constrict blood flow in an area. So sometimes you just have to kind of make the vein small enough, and then that increases the resistance so much that that blood flow can't get through. Okay. This also has an effect on the local velocity inside the vessels as well. And so, if you imagine kind of what the fluid flow looks like in a nozzle, so when you have a nozzle and fluid is kind of constricted to go through the nozzle, it's going to increase the velocity of the fluid going through just because of conservation of mass considerations, right? And so this of course affects kind of the fluid mechanics and kind of the wall shear stress in the veins as well. Okay. So here's kind of an example of this. And so this image is a little bit difficult to see, but basically what's happened here is that, you know, this kind of dark blue part right here, this right here is a muscle. Same thing for down here. And what you can see is that this muscle is kind of contracting. And so what that's doing is that it's constricting the blood flow. And so that when the blood flow goes through this this orifice here, you can see that it's speeding up, right? And so it goes from this light green color, which is kind of relatively slow velocity, to this deep dark red color as it passes through. Okay. And so you see this happen all the time in your veins because, you know, depending on your posture, depending on how you're leaning against things, depending on, you know, if you're putting pressure on your veins, something like this can happen all the time, even without you really noticing. Even just kind of flexing a muscle, you know, can cause the veins to kind of partially collapse and accelerate the blood flow. Okay? But what's interesting is that, you know, your muscles contracting actually provides another important function for the veins as well. And so, you know, you may look at this and think like, oh, you know, like I want to be careful, you know, I don't want to constrict my veins, but constricting your veins and unconstricting them is actually a very important part of how the cardiovascular system works. And your muscles actually play a very important role in actually getting the blood back to your heart through the veins. Okay, we'll talk a bit more about that a bit later. Okay. All right. Any questions on this? Okay. All right, so let's talk about the concept of venous return. Okay? So venous return is a clinical parameter, okay, which talks about the amount of blood or the volume of blood that returns to the right atrium from the systemic circulation. Okay, and so you know, after your blood goes through your muscles and organs, and so this part right here, the systemic circulation. Remember, these are all your muscles and organs, right? Okay. After it passes through there, then it has to return to your heart, right? And so just the raw volume of blood that returns to your heart through the veins is called the venous return, okay? And obviously, you know, you have to maintain a healthy venous return just to ensure that the heart has a continuous supply of blood to pump to the lungs and then to pump to the rest of the body, okay? And so it's kind of almost the same thing as cardiac output. And under stable conditions, so let's say that you're at rest, the venous return should equal the same thing as the cardiac output, because how much of blood leaves the heart should be the same amount of blood that comes back to the heart, you know, under conservation of mass. Okay. But they can be different under certain situations. So, like let's say when you're exercising, or let's say that, maybe you have a lot of venous collapse. So let's say that you're in a position that's constricting your veins. Your venous return may be affected in those cases, right? So you may have a lot of blood that's kind of pooling in the veins where, not enough blood is returning to the heart. Okay. Okay. And so the venous return here is directly affected by the health of your veins. And so it's affected by things like the pressure gradient, the resistance of the vascular bed, and the influence of the calf muscles as well. Okay. Not just the calf muscles, but all the vessels in your body, or all the muscles in your body, excuse me. All right, so let's talk about that a little bit. So let's talk about the calf muscle pump. So this is actually pretty fascinating. So like we know, like we mentioned before, right? The flow in the veins is incredibly slow, right? And actually, a lot of times the veins themselves don't have enough energy to get the blood back to the heart after it passes through the cardiovascular system. Okay, so the heart itself can't provide enough energy to get the blood through the arteries and through the veins at the same time, right? So your veins actually get a little bit of help from all the other muscles in your body. Okay, kind of the biggest example of this is in your calf muscle. Your calf muscle is kind of on your lower leg in the back. And what happens is that as you contract your calf muscle, it actually squeezes this very big vein that goes through your leg, right? And then as this vein gets squeezed, it kind of pushes blood up back to the heart. And so the heart is kind of up here. So this is actually a very important mechanism in your body. So your body actually relies on the muscles inside your calf, as well as the muscles in other parts of your body, to kind of squeeze the veins every now and then to kind of help push blood back to the heart, right? Some people even consider your calf muscles to be kind of like the second heart, because it kind of provides the same thing, where it provides a lot of squeezing action in order to get the blood back. And that's kind of what's needed to operate, right? So if you've ever heard someone give you the advice where if you need to kind of increase the circulation in your body, or improve the circulation, to take a walk, right? And so if you take a walk, obviously you're stimulating your leg muscles and so on. And so stimulating your leg muscles, getting them to demand more oxygen, that's part of improving your circulation. But the other part that I think people don't really realize is that as you kind of walk and you kind of contract your calf muscle and you let it relax, you're actually also increasing circulation just by the fact of you're squeezing your blood vessels to push blood further. Okay. And so as you kind of walk and you take steps and your calf muscle contracts, it relaxes, it contracts, it relaxes, then it also kind of pushes blood. And this actually helps push blood, processes blood through your entire system. So that improving your circulation improves just a lot of things. It gives you more energy, it gives you better waste removal, things like that. Okay. And one thing that helps with the veins here is that your veins have all these tiny little valves inside as well. And so when you squeeze, right? So let's say that, let me go ahead and draw right here, right? So let's say that you squeeze a vessel, so that looks like this, right? And so when you squeeze, the blood's going to go this way. When your calf muscle relaxes, to make sure the blood doesn't come back, there are valves inside your vein to prevent any kind of backflow, right? So when you squeeze, it pushes blood through, and then once the blood pushes through, then the valve closes, preventing the blood from going back the other way. Okay. And so sometimes, what you'll see doctors do is that, if you need to kind of improve circulation, or you need kind of help with that, they actually have you do calf muscle stretches. So you stretch your calf muscle, you contract your calf muscle, you do exercise with that, and that really helps to get the blood back, right? Because your legs are actually the hardest part for your veins to return from, because your legs are so much further down compared to your heart. Then there's not only is the blood in your legs working against viscous resistance, but it's also working against gravity as well. So that's why the blood in your legs, really needs the help from your leg muscles to help get the blood back up there when it needs to. Okay. All right. Any questions on this? Okay. Okay. So another such pump inside your body is the respiratory pump. Okay. And so the respiratory pump is another kind of muscle related pump inside your body, but it's from your diaphragm, right? So the venous pump, or excuse me, the respiratory pump helps aid with the venous return, right? So as you breathe, right? So the way that you breathe is that your diaphragm muscle kind of pushes up and pushes down on your lungs. That action also helps to improve the circulation through your veins as well. Okay. And so that squeezing motion where you squeeze your diaphragm, you breathe in, you breathe out, right? That also has a similar action of squeezing the veins and helping blood flow go through. Okay. And of course, as you exercise, your diaphragm muscle is going to go faster as your body demands more oxygen. But then as your diaphragm kind of contracts faster and faster, that also helps to improve blood flow as well, right? It's a very synergistic system where your respiratory system also helps your cardiovascular system, and your cardiovascular system helps your respiratory system as well. Okay. The human body is very fascinating. So there's a lot of these kind of synergies inside the body, and it's kind of amazing that all this kind of mechanisms and mechanics are kind of jam-packed within a human body. Okay, so let's talk about the valves a little bit more. Okay, so the venous valves, these are the valves that are inside your veins. They act very similarly to the heart valves inside your heart. Okay? So we know that your heart has a lot of valves inside it to kind of help regulate the blood flow through your heart, right? To make sure that as your heart contracts, there's no blood that goes backwards. Everything's going in the right direction, and the operation of those valves is important for good cardiovascular health. The venous valves are the same way, although they're not as critical as the heart valves. So the heart valves are very important because your heart is the most important muscle of your body. The venous valves play an important role, but they're not nearly as important. But they serve the same purpose, right? And so the point of the venous valves is that when blood flows through them, they make sure that blood doesn't go back, right? Because if blood was able to go back through the veins, it's going to take a lot more work from your heart and from the rest of your muscles to get the blood through. So the valves are there to kind of help improve the efficiency of the system and kind of minimize the energy output. Okay. But the locations of these valves are interesting because even though for the heart you have them in kind of very specific places, for the veins, these valves are actually littered all throughout the vein itself. Right? So if you have a relatively long vein like this, so let's say this is the vein inside your calf muscle, you're going to have valves kind of at various different points inside the vein. So each of these kind of horizontal lines that I drew here is a vein. Okay? And so that just basically makes sure that when blood goes through, it doesn't come back. Okay. And these veins actually have a very kind of interesting applications too. So I'll kind of sidetrack a little bit and talk about a project that I worked on in grad school. So in grad school, I worked on simulating coronary bypass surgeries. So those are surgeries that people undergo when they have a lot of disease around the heart. Right? And so sometimes in that surgery, what they'll do is that they'll take a vein from one part of your body and then graft it near your heart. Right? So they're basically taking a redundant blood supply and then adding it to your heart to help kind of improve the circulation there. Okay? But one thing that they have to do is you're based and which is kind of interesting because you're taking a blood vessel that's accustomed to the venous system, so it's accustomed to seeing low blood pressures, low blood flows, and you're suddenly putting it in an environment with very high pressures and very high flows. So the veins are actually not really well adapted to those conditions. And one of the main culprits is the valves. And so when you expose these valves to kind of very high flows and very high pressures, they may kind of seize up and not really work as intended. And so one thing that the doctors actually did, and for the untrained eye, it's impossible to see, is that let me kind of draw you an image just so you can see. So let's say that you have a heart like this, right? But and then you have an aorta that comes out, so the aorta looks like this. Okay. Go to space. right? So that's your heart and the aorta. And let's say that, we need to get blood to this part of the heart right here, okay? So what's usually done is that we do something called a bypass graft. So you take a blood vessel from another part of the body and you attach it from the aorta, right? So you have one attachment site here, and then the other site you attach down here, okay? Because what this does is that now when the blood comes out the heart this way, some of it is going to be redirected through this graft, and it's going to get to this part of the heart muscle, which may need, okay? Because maybe the native vessels, because normally the heart has some vessels on the outside, right, that reaches this point, but maybe this heart vessel, maybe this blood vessel right here gets clogged up due to plaque or something like that, or atherosclerosis, and so you need to do a bypass graft to go around it. Okay? One thing that the doctors always did, so let's say that this extra blood vessel, they obtained this blood vessel from the veins. Okay, very common because you have a lot more redundant veins in your body than you do arteries. And so what the doctors would actually do, just to make sure that the valves don't get in the way, is that they would put the vein on backwards. And so normally you would think that the valves would go like this, and the valves would open up this way, right? They would actually flip it backwards, so the valves are just not an issue, right? And so then the valves would kind of open like this. And because they're kind of on backwards, they kind of stay permanently open, so they don't really ever close. And so it's kind of a clever way to kind of use a vein in this situation to kind of minimize the chance that it would seize up, right? So you have valves that kind of go like this. But I actually went into the hospital to actually see one of these operations, and it was kind of impossible for me to tell, whether the vein was on forwards or backwards. And the doctor kind of like, tested me kind of right there on the spot to say, like, can you tell which way this vein is going? I'm like, I can't tell. And so he showed me the valves on the inside to make sure they're going the right way. So yeah. Yeah, but the venous valves they serve a very important role, but they only really work in the venous system. And so if you're going to take the vein out from that, then you have to adjust it accordingly. Okay. All right. Any questions on this? Okay. All right. So let's talk about the geometry of the venous valves themselves. Okay. So the geometry of the valve is actually very similar. So the way these valves work is that they have these two what are called leaflets. Okay. So normally for the valves inside the heart, for the most part, the valves in the heart have three leaflets, right? So if you look at kind of a cross section of the valve, it kind of looks like this. We have kind of three valves that kind of like this. So this is leaflet 1, leaflet 2, leaflet 3. Okay. And so when they open up, so if you look at kind of a cross section, right, the leaflets kind of open up like this. Okay. And there's kind of a third leaflet that kind of goes up like that. Okay. So most valves in the heart are three leaflet valves. The difference in the venous valve is that there's only two leaflets. So if you look at kind of a cross section, so here we're kind of looking at a sideways cross section. If we look at kind of an axial one, it looks like this, where there is kind of a one leaflet that goes like this, and another leaflet that's kind of opposite it. So you have 2, 1, 2 like that. Okay. And so when they open up, they kind of open up kind of like a blossom. So they kind of swing their doors open, and then blood kind of flows through them. And so when you look at them from a cross section, it looks like this. Okay. Okay. The other thing to know, just kind of some trivia, is that venous valves have a very pronounced sinus. Okay. And so the sinus is the region right after the valve. Right? And so you can see that whenever you have a valve, the blood vessel kind of is a little bit almost kind of like expanded, or there's kind of like a little bit of a bulb there. And so that right there is the sinus of the valve. So that's kind of the immediate area where the blood flows into after it goes through the valve. Okay. So this geometry actually has some very important implications for the flow through the valve, right? Because as you can imagine, the blood, as it's coming through here, because the valve leaflets don't often open up all the way, the valve leaflets themselves kind of almost act like a little bit of a nozzle, right? So the blood kind of converges here, and then as the blood goes through the leaflets, it kind of speeds up a bit. Okay. All right, and so that kind of has some really interesting patterns as well. And the other thing that could happen through the vein, it's not as common just because the flow rate is small, is that you may get little vortices inside the sinus like this. Okay. but maybe during exercise or something like that, those vortices could be more pronounced. Okay. So a lot of the information that we know about venous valves is actually through simulations. So just because the flow is really slow there and it's a lot harder to image, we don't have a lot of kind of hard data on the flow that happens in the veins. Okay. One thing that we do know is that the valvulus don't open all the way, right? So like I mentioned before. And so this causes kind of a local constriction of the blood flow, even when the valve is fully open, right? So that leads to a lot of increased velocity going through the valve and a lot of local flow recirculation. Okay. Yeah. So the venous valves, there's a lot of them. I think there's not even a reliable count in terms of how many venous valves a typical person has. But they're all there just to make sure that the blood gets back to the heart as intended. Okay. All right. Any final questions on the valves? Okay. Cool. All right. So let's talk about posture. So unlike the arterial system, where the flows and pressures are so high in the arterial system that it doesn't really, it's not really affected by your posture. The venous system is affected by things like hydrostatic pressure. And so depending on the posture of your body, it's going to affect the amount of flow that goes through your venous system. And so if you remember from your fluid mechanics class, very, very early on, the first thing that you learn in fluids is this idea of hydrostatic pressure, okay? Where hydrostatic pressure is the pressure that exists in a fluid just by the fact that it's underneath the column of a bunch of other fluid, okay? So if you measure the pressure of the fluid at this location here versus the fluid here, right? This pressure here is going to be a lot higher just because there's just way more fluid that's on top of it, right? So the pressure is almost an expression of the amount of weight of the fluid that's kind of on top, right? And so there's a very simple formula that you can use to compute the static pressure, which is rho, the density, multiplied by gravity, times the height of wherever it is, okay? So this has a lot of implications for the venous system. And so because of the relative position of your limbs or your veins relative to your heart, it can change the amount of blood flow that happens in your veins. Okay. So probably you guys are familiar with this, where if you take your hand and you raise it above your head and you kind of keep it there for a very long period of time, your hand starts to get tired. I mean, your muscles get tired because you have to kind of hold that position. But another reason why it's difficult is that your fingers start to feel all kind of tingly, right? The reason for that is because as you raise your hand higher, it gets harder and harder to kind of push the blood up there and for it to kind of come back afterwards, right? And so this kind of change in hydrostatic pressure has a big influence in terms of how the flow in your veins occur. Okay. All right, so here's some kind of images of the flow in the veins, right? And so as you go from left to right in this image right here, on the left here, this is kind of the ideal situation where your hand is kind of below your heart, okay? And so in those situations, the hydrostatic pressure kind of helps you because it kind of gets the blood through there and it comes back, right? And then as you raise your hand, so in image B, this is an image of your hand kind of at heart level. And then when you raise your hand up to your head level, you can see there's kind of less and less blood inside the vein because it gets harder and harder to pump blood through them because of the hydrostatic pressure. Okay. All right. So that's kind of the basics of kind of blood flow in the veins, right? And so not nearly as interesting as arterial flow, but there are kind of a lot of interesting things, right? Like the valves and the influence of posture and the venous collapse and all this. Okay. So the last thing I want to do today, so obviously we're gonna end pretty early today, is we're gonna talk about a few different diseases that can occur in the veins. Okay. So the first disease that can occur is something called venous insufficiency. Okay. So venous insufficiency is a disease where you have very poor venous return. So the blood is having a very hard time coming back to the heart, right? So in these situations, your heart has no problems pumping the blood to your muscles and organs, but then after it gets there, the blood has a very hard time coming back. Okay. In particular, the most difficult place for it to get back from is the lower limbs, just because of the effect of gravity, right? And so usually, if you have some issue with the veins in your lower leg, that can affect the venous return of the blood through, back to the heart. Okay. So usually this is diagnosed by abnormally high pressure in the lower limbs, or you might see some of these other symptoms here where you have some pain and heaviness, restless leg, a lot of leg cramps, a lot of itchy skin in that area, right? So these can all be symptoms of kind of poor venous return in your legs. Okay. So the underlying causes for this are kind of still a topic of research. So I think we still don't know very much about them. Okay. But there have been complications that if you have some kind of ulcers in your lower body, something called edema, which is fluid retention in your lower limbs, and fibrosis, which is if you have a lot of scar tissue in your legs as well. Okay. So usually the main means of diagnosing venous insufficiency is to use an ultrasound. Okay. And so they may detect things like maybe lack of valves, maybe there's some blockages that are occurring, or just maybe there are some anatomical impediments that prevent the flow from returning from the lower limbs. All right. Another disease that's very common, or not that common, but people know about it, is something called varicose veins. And I think just a lot of people know about this just because you can visually see it oftentimes on people. Okay. So you might have seen varicose veins before. People with varicose veins have these kind of very kind of pronounced, kind of thick blue veins that appear on their legs. Usually these are kind of, people consider them quite unsightly. So I think people try, not really to solve the issue, but to cosmetically kind of get rid of them so that they don't show up. But they are a health issue, right? So varicose veins, the exact definition for these are, swollen and twisted veins that are visible just under the skin. Okay, because for the most part, you can't really see most of the veins inside your body, but varicose veins get so swollen that you can actually see them on a person's body. Okay. So varicose veins is like another one of those things, just like a lot of venous diseases, we don't really understand them all too much. We kind of understand a little bit how to fix them, but how they happen, why they happen, or why they happen to certain kinds of people, is still kind of a cause of, it's still a very hot topic of research. Okay. So some hypotheses out there is that, varicose veins may be a result of valve failure. And so the valve failure can lead to kind of an expansion of the vessel walls, which can kind of lead to varicose veins. Okay. Another change, just because, varicose veins have been linked to aging. So typically you see them more in older people than younger people, is that a change in the material composition of the vein wall, maybe increased collagen, has also been kind of hypothesized as an issue. But it's still very much kind of a hot topic of research. Okay. So the last topic that we'll talk about today is something called deep vein thrombosis. So this is kind of one of the more serious conditions that can happen in the veins. Okay. So deep vein thrombosis is a condition where a blood clot or a thrombosis forms inside the veins. Okay. And this thrombosis is usually bad because usually you only want your blood to clot wherever there's a wound. And if you have a blood clot that occurs kind of in the middle of your vessel without anything prompting it, it can cause blockage of the heart, of the blood flow itself. Okay, especially if it occurs somewhere next to a valve like this. Okay, or even worse, what can happen with a lot of thrombosis is that normally thrombosis occurs and it's attached to the vessel wall, but a lot of times in the worst cases that thrombosis can actually detach. And so you have this kind of glob of kind of really sticky and kind of solid blood that's floating through your system. And then if this gets to a very critical part of your body, so let's say it gets to your brain, or let's say it gets to like a very thin part of your heart, it can block the blood in a very crucial part. Okay, because usually if you have a thrombosis down here just by itself and it stays there, it's usually not the worst thing in the world. But the main concern with clots is that they kind of detach and go somewhere else. Okay, so generally speaking, you just don't want blood clots in your body at all, unless it's to kind of fix a wound. So the scary thing about deep vein thrombosis is that it's mostly asymptomatic, so that means you don't really feel anything. But sometimes what can happen is that the person's legs will tend to swell. Right? So like most vein diseases, they mostly happen in the legs, just because those are the parts where the blood really struggles to get through the veins. Okay. Okay. And so, like I said, the most severe consequence happens when the thrombus detaches. It can cause like a major event, like a stroke or a heart attack. Okay. So, even though, we still don't really know that much about deep vein thrombosis, we have been able to study, some cadavers or people that have passed away from it. And what we do know is that, what we do know is that the deep vein thrombosis tends to form at the locations of the valves. Okay. Which makes a lot of sense because the fluid mechanics in the valves, the blood flow kind of gets stuck in the valves a little bit. It has to kind of accelerate. And so it kind of makes sense that that the thrombosis kind of forms there as well. Okay. And so, there's a strong link between the fluid mechanics of the blood flow through the venous valves and the cardiovascular disease. So this is something that could be explored with simulation. Okay. And so another thing that people have found is that your risk of thrombus formation kind of increases if you have long periods of inactivity. Okay. And so if you sit on the couch all day, you're not really engaging your muscles. What tends to happen is that your blood tends to stagnate inside your veins. And whenever you have any kind of blood stagnation, that kind of increases the risk of thrombus forming. And so you want to make sure you still live a relatively active lifestyle. You're still getting around. You're still walking, just to kind of prevent some diseases like this from happening. Okay. All right. Any questions on this? Okay. All right, so that's all I got for today. So these next 3 lectures are all going to be pretty short, so I expect all of them to probably end pretty early. So when we come back on Tuesday, I have another set of lecture notes on the microcirculation, and so look forward to that. And then I'll have your exams ready for you on Tuesday as well. But I think what will happen over the next couple lectures that the lectures will probably end early like this. I probably only have about 45-50 minutes per lecture, and so what I'll probably do is that I'll use the rest of the time to help you guys with your projects. Okay? So if you haven't tried to do a mesh on your project yet, I would definitely tell you to do that. I suspect that probably a lot of people might have some trouble with the meshing, so you want to make sure that you give it a try and then give yourself enough time to ask for help from me. Okay, bring it to class, have me look at it, and then we can get past that, and then we'll kind of keep working that over the next few weeks. Okay, all right. So thank you guys for coming today. I know it's the day after the midterm, so I appreciate you guys coming. Hope you guys have a good weekend, and I will see you guys next week.
Not to the, but sure.